Hello everyone. In this video I am going to demonstrate single sideband suppressed carrier amplitude modulation and demodulation technique with non-coherent detection. As compared to the previous video, in the previous video I was showing coherent detection. I was using envelope detector as the coherent detector. So now in this video I have modified the circuit. You can see here this is the transmitter part and this is the receiver part. On the transmitter part, here is a tone generator and a carrier frequency generator. So the tone generator frequency output is mixed with the carrier frequency output, and finally we are getting single sideband waveform. So this waveform is fed to the ring modulator here, and the output of the ring modulator is filtered with the low pass filter. So on the ring modulator, both the two inputs, I am using the same carrier frequency, the same modulated signal. Let us look into the circuit diagram. The wiring will be very clear. As you can see, this is the modulator part. This is same as the previous video. Is same as the part 1 of this single sideband suppressed carrier series. This is the, from here we are getting the single sideband suppressed carrier output. So this is the real amplitude modulated wave. So this amplitude modulated wave is fed to this ring modulator here. This is basically a mixer, the ring modulator. So you can see here the same wave is fed to this point and this point. So upon mixing and upon filtering, we are getting the original signal. So let us look into the mathematical derivations. Here you can see AMT is the message signal and carrier signal is cos omega ct. So when we are multiplying these two signals in the transmitter here, we are getting the output AMT cos omega ct. So this is the single sideband suppressed carrier waveform AMC cos omega ct. This is the waveform. So now this waveform is fed to this mixer stage here. So in this mixer stage, what's happening, you can see here on the two ends of the mixer, the same waveform is fed. That means A cos omega ct, AMT cos omega ct is multiplied with the same signal. So when they are multiplied the signal is multiplied with itself and we are getting this output. Finally, when we derive this formula, we are getting this complex mathematical form. So if we filter this mathematical form here with this low pass filter, we can see here AMT cos omega ct. This is the original message signal left. So the message signal appears here. Let us look into the oscilloscope. We will be observing the message signal at the output. As you can see here, this is the single sideband suppressed carrier waveform. You can see 450 Hz this is the 450 Hz signal and 45 kHz signal is encapsulated inside. Upon filtering this signal, we are obtaining this signal. So this is basically the 450 Hz original signal. The waveform, you can see there is some capacitance effect. This is because of the filter. The filter is not designed correctly, so that's why there are some errors. You can see the signal is not very nice, very sharp. This is because of the filter. I am using an analog filter, so that's why due to the resistance capacitance combination I am getting this effect. Also, this waveform amplitude is very weak. I cannot hear it on the speaker. I can hear it, but the amplitude is very low. So this means this type of detection needs an amplifier stage to detect the real signal. In the previous video, I was able to detect the signal very easily and very nicely. The sound was quite high, but here the sound is very low. This is because you can see in the mathematical formula, the real message signal is divided by a factor of 2. You can see that's why the amplitude is really going down and it is difficult to listen, but it is audible. So let us try to connect it with the speaker and we will be trying to listen the signal. I connected the signal before the low pass filter. That's why the sound output was pretty high. Now let me connect it after the low pass filter. The sound is very weak. I can hear the sound, it is audible, but it is very weak. So it is concluded that coherent detection is very easy and cheap method of detection for AM radio principles. In the next video, I am going to enhance this non-coherent detection. I am going to enhance this non-coherent detection technique, and I will be using a local oscillator and we will be observing the results. Here I have multiplied with the same signal, the main signal with itself, but in the next video I will be multiplying it with a local oscillator. So we will be observing the differences. Thanks a lot. Thanks for watching.